Okay. Okay. I will share these notes in the e-learning after the class. Okay. And tomorrow I will share the recorded version. Okay. So figure. Okay. Actually, I obtained this note from DAS reference book. Okay, so I could not change the figure number. Okay. So when we look on the figure 10, 14, okay. So this is the diagram for an embankment. Okay. So then we want to determine, okay, what is the stress, okay, at a certain depth of Z. Okay. So later on, when we obtain the value, okay, we should multiply with 2, okay, by imaging both of the width is similar. Okay, so that's why we can dissect into 2 or cut into 2, okay, area. Then later on, we may multiply with 2 to get the actual load or stress. Okay. Figure 10.14 shows the cross section of embankment of height of H. Okay. So this is the height of H. Why we need the height? Because we want to determine what will be the Q naught. Okay. So the height should represent the maximum height. Okay. Then multiply with the unit weight of soil. Okay. Normally, the unit weight of soil is range between 17 to 18.5 something. Okay. So then we multiply. So that will represent the Q naught. Okay. So by using this formula, okay. So we have here B1. Okay. B1 if the width of the flat area, okay, or flat structure. Then we have a B2, okay, is the width of the slope area. Okay, so this is the common typical type of embankment. Okay, so divide with B2. Then we have alpha 1, okay, which is the degree angle, okay, from the edge of the B1, okay, and from the starting point of the B1. Okay, so that will be alpha 2, okay, and for the alpha 1, okay, so the alpha 1 is the distance, is the degree, or is the degree, okay, which is represent from the length from the toe to the top of the embankment slope. Okay, so that is alpha 1, alpha 2, okay, minus with the B1 over B2 times alpha 2. Okay. So this is some the explanations, okay, on the derivation of the alpha 1 and also alpha 2. Okay. So please carefully use a radian value, okay, do not use a degree, okay, because you cannot multiply a degree with a normal number. So you need to change into radian. Okay. So if you want to get more explanation on how to derive the equation, okay, so you may look on the DAS 2008, which is the Advanced Soil Mechanics books. Okay. I have the books, okay, if you want, so I can share with you the DAS book. Okay. A simplified form of equation, okay, so later on it will become like this, okay. Why they produce this kind of equation, okay, because they have a chart, okay, developed by Ostomate, okay, in 1957. Okay, so this chart, okay, I guess all of you are familiar with the normalized chart, okay, because we have used a lot, okay, in our previous example. Okay, So this is the Ostomate chart, okay, where we can determine the I2. Okay, so the I2 basically is the function of B1 over Z, okay, and B2 over Z. Okay, how to determine the I2? Okay, for example, we calculate first what will be the B1 over Z, okay, which is the width of the flat surface of the embankment over with the Z, the depth of the uh, desired depth that we want to investigate. Okay, so then another one will be B2 over Z, okay, which is the width of the slope area over the Z. Okay. So then we can determine the I2. Okay, later on the I2 we may multiply with the Q naught. Then we may obtain the increment of stress at certain level. Okay. Okay. So what is the importance of this Z? Especially on the settlement calculation. Okay. We should determine the Z or the depth, okay, which is influence the settlement, especially in the soft clay area. Okay, we may discuss later. Okay. Okay. So so we have two calculation here. Okay. The 10-20 equation. Okay. Another one by using this Ostomate chart. Okay. So now we look on, okay, actually this equation, okay, Ostomate, okay, this 10-20, okay, we can easily get the increment of stress at the center of the embankment, okay. Definitely the most highest strength, okay, actually at the center of the embankment, okay. However, if the question asks, okay, for us to determine what will be the strength or what will be the stress at the edge of the embankment, we still can use this Ostomate or the 10-20 equation. Okay, so now we look on one example, okay, which is we want to determine what is the stress, okay, 6 meter below the toe of embankment located at A. Okay. So when we look on this embankment, okay, the geometry of embankment is not symmetry, okay, especially on the width of the slope. Okay. So this is one vertical over 1.5 horizontal, while another side is one vertical over 2 horizontal. Okay. Let's say if you want to determine what will be the stress at the center of the embankment, okay. So we need to have two solution where we calculate first the left area and then continue calculate for the right area. Then we plus both of the result. Okay. But compared to a symmetry problem, we just multiply with 2. Okay. So an embankment is shown in figure 10.16a. Okay. So this is the problem. Okay. Determine the stress increase under the embankment at point A. Okay. So how to solve it? Okay. So we need to use the same procedure like the FEDEM, okay, where we need to create a dummy area, okay, which is represent this 10-16b, okay. Then later on we may deduct with the 16C. Okay. Okay. So I guess, okay, this diagram or this chart is only capable, okay, to solve the problem which is related to this diagram. Okay. In that sense, we need to make sure that all the problem similar like this diagram. Okay. So in that case, that's why for the 1016B, okay, so they have a full flat area, okay, with the rest is a slope length. Okay. So in what we call in actual condition, this part is still it's shown as a slope area. Okay. However, when we want to use the equation from the Ostomate, we want to use the chart from the Ostomate, so we need to imagine, okay, this is a flat surface, okay, with a slope of 20 meter width. Okay. So when we when we have this full flat surface, okay, so the B2, okay, so okay, we look on this diagram, okay, so the B1, okay, will become 21, which is 15 plus 6. Okay, so that is the B1. Okay, then divide with 6. Okay, why 6? 6 is the D value or Z value. Okay, so 21 over 6 is equal to 3.5. Okay, so that is for the 10.16B. Okay. So we need to remove the area which is not existed. Okay. So then we or logically, okay, this what we call as this portion, okay, will become like this triangle, okay, without having any flat area. Okay. So it will represent as a C. Okay. So 3.5 for the B1 over Z, 3.33 for the B2 over Z. Okay. So we may refer to this diagram to determine the I2. Okay. So for the first 1016B, okay, the I2, okay, will become 0.495. Okay. So you may check later, okay, by looking on this diagram, or we can try, okay. For example, B1 over Z, B1, okay, this is B1, okay. The value is 3.5, okay. So it reached almost on the maximum value, okay. Then we have another one, 3.33, okay. So 3.33, okay, 1, 2, 2, 3, okay, here. Or we can use this one, 1, 2, 3, 3.33 something here. So approximately it is equal to 0.50. The answer. Okay, so it show 0.495. Okay, or we can use 0.5. Okay. So that is for the 1016B. Okay. Now we look on the 1016C. Okay. So for the 1016C, with the B1 is equal to 0, okay, divide with Z equal to 6, so it becomes 0. Then for the 15 over 6, the B2 over Z will become 2.5. Okay. So when we look on this diagram, okay, so B1 over Z is 0, B2 over Z is 2.5. Okay. So later on, the Iz or I2 will become 0.39. Okay. So 0.5 here, I2 becomes 0 point something, 0.39. Sorry, I2 is 2.5, 2.5, 2.5. Okay, here 2.5. Okay, 2.5. So you need to use a ruler. Okay, then you will gain 0.3 something. Okay, so for this answer 0.39. Okay, so then 180 is the Q value. Okay, where the maximum height, okay, 10 times with the 18. Okay, 18 is the unit weight of the soil. Okay, 180. So times with the difference between sigma Z1 minus sigma, sorry, I1, I2 1 minus I2 2. Okay. So then 0.49 minus 0.39 multiply with 180, it become 18.9. Okay. So that is the solution, okay, to determine what is the increment of stress at this point. Okay. Okay. However, when we want to calculate for bearing capacity or to calculate for the what we call it for the settlement, okay, so we should use the maximum or the highest strength or the highest stress which is located at the center of the embankment. Okay. Okay, any question?
Yeah.
Okay.
Clear.
Clear? Okay. Okay. Now we move for the settlement.
You got there?
Anak saya kacau. Dia tutup bising. Okay. So now we move for the example for the settlement. Okay. Okay. So the soil profile of a proposed project site is shown in figure 1. Okay. So this example is for the settlement calculation. Okay. It is to calculate for the primary consolidation only. However, for the immediate settlement, okay, I'm not included in this example. Okay, later on we share in the e-learning. Okay, because the most critical value for the settlement occur during the primary consolidation. Okay. So a soil profile of a proposed project site is shown in figure 1. Okay. 100 meter times 200 meter embankment of 5 meter height will be placed on the ground surface to compress the clay layer. Okay. So I'm highlighting the clay layer. Okay. Because the primary consolidation only happen at the clay layer. Okay. So the embankment material is soil with a unit weight of 18. Okay. Determine the settlement due to embankment. Okay. So in this case, okay, either we can use the Ostomate approach or we can use the 2-to-1 method to estimate the stress increase, okay, when necessary. Okay. So okay. So this example of an equations, okay, for the 2-to-1 methods. Okay. So this is the diagram for the 2-to-1 methods. Okay. So refer to the diagram shown below to estimate the increase in stress. Okay. The equation derived from the diagram is expressed as QBL over B plus Y or Z times L plus Y or Z. Okay. So in this case, we use Z to represent the depth. Okay. So, okay, while this is the properties of the soil, okay, we have a silty sand with a different of soil properties due to the groundwater level. Okay. And the next layer is the clay, okay, with a unit weight 18.3, okay, specific gravity 2.6, water content is equal to 35, okay, and then C is equal to 0.4, while CR is equal to 0.04. Then the clay layer is overlain the sandy gravel. Yeah. So in this case, okay, we may use equation which is represent a normally consolidated condition. Okay, why we use the normally consolidated condition? Okay, because previously, okay, before for any construction of the embankment, okay, there is no any structure or any loading on the top of the ground area. Okay, so we consider the previous and the current effective stress is equal. Okay, so that's why we consider as a normally consolidated condition. Okay, unless, okay, before we carry out the test or before we carry out the construction, okay, we need to remove a certain height of material, okay, on the top of the ground level. Okay, so in that case, the prehistorical or pre-consolidation pressure is greater than the over-consolidated effective stress value. Okay, so that is how we differentiate between normally and also the over-consolidated situation. Okay. Okay. Okay, before we start to calculate for the settlement, okay, so we may refer to the normally consolidated equations. Okay, so this is a normally consolidated equation. Okay, so in this normally consolidated equation, okay, we have here H naught, which is the height of the clay layer, which is 16, okay, over 1 plus E naught. Okay, the E naught we may calculate from the GS and the water content. Okay, so then we have a CC there. Okay, so we may use the 0.4 for the CC. Okay, then we also need to calculate what is the effective vertical stress. Okay, so this value, okay, is the unit weight of the silty sand multiply with the height, okay, and also the mid value for the clay layer, okay, multiply with the mid height. Okay, why we use middle height? Because if we use a full height, so it may overestimate the settlement value. So the value for the middle height is 8 meter. Okay, so we need to calculate what will be the effective stress, okay, from the top, okay, to 3 meter, continue with the 2 meter, and the last one is 8 meter. So in total, 5 times 8 is equal to 13 meter height. Okay. Okay. So the last one is the delta sigma. Okay, the delta sigma is determined by using the 2 to 1 method. Okay. So first look at the delta sigma. Okay. We have here Q, BL over B plus Y, L plus Y. Okay. So the value of the Q, okay, is equal to 5 times 18. Okay. So 5 times 18 is the Q. Then we may multiply with the width and multiply with the length of the embankment structure. So the length and the width is 100 times 200 meter. Okay. So B is 100 plus Y is 13 times 200 plus 13. So later on, the value is of the delta sigma is 74.78. Okay. So that is for the delta sigma. Okay. So the situation can be considered as normally consolidated condition, and the equation used as below. Okay. So this is the equation. Okay. Then we may continue to calculate for the sigma naught, which is the effective stress. Okay. So 17 times 3 plus 18.5 minus 10, which is the unit weight of water, times 2, then plus 18.3 minus 10 times 16 over 2, which is the height of the middle length. So the value of the sigma naught or effective stress is equal to 134.4. Okay. So this is effective stress. So the value for the initial void ratio, E naught, to be used in the equation above can be found using the following relationship. Okay. So this is the common equation. Okay. To determine either W, G, S or E naught. Okay. So for this case, we want to get the E naught. Okay. So we have been provided with the W and GS. Okay. So due to the soil is under the groundwater level, so we assume the saturated degree, which is the SR, is equal to 1. Okay. So from there, E naught is equal to WGS. So it will become 0.91. Okay. So by substituting value into the consolidation equation, okay, so the delta H is 0.64 meter. Okay. Looks like the value is very high. Okay. So what should we do? Okay. Either we want to reduce the height of the embankment, okay, or if it is defeat the purpose, so then we may do a treatment, okay, to strengthen up the consolidation characteristic, or we may improve the settlement performance by using a treatment methods. Okay. So there will be two options there. Either we want to reduce the height of the embankment, okay, or we may use a treatment, okay, to enhance the consolidation characteristic of the soft clay. Okay. So that is for the embankment calculation. Okay. Any question for the number for the settlement? Okay, no. Okay. So I will stop this recording first.